Calculate our CaO2 content. Content is all about hypoxia, tissue oxygenation. Hypoxemia is partial pressure. So the CaO2 is equal to the amount bound in hemoglobin added to the amount dissolved in plasma. And it's always equal to the hemoglobin times 1.34 times the SaO2. Notice that we're looking at the arterial content, CaO2, SaO2, added to 0.003 times the P(a)O2. So in arterial content, we're interested in the hemoglobin, the arterial saturation, and the arterial oxygen partial pressure. In mixed venous content, where do we take a mixed venous blood gas sample from? From the venous system, where specifically? Mixed venous. We should be from the Swan-Ganz catheter in the pulmonary artery. So we can draw a blood gas sample out of that hemodynamic catheter and measure the content of mixed venous blood. So it's both, the amount bound to hemoglobin and the amount dissolved in plasma. And the CVO2 content of mixed venous blood is the mixed venous hemoglobin. Every gram of hemoglobin carries 1.34 milliliters of O2 times the saturation in the pulmonary artery, the mixed venous saturation. And at the end of that catheter that we looked at last week, there's a pulse oximeter, and it measures saturation in the pulmonary artery. So the SVO2, what's normal SVO2? Does anybody know? Normal saturation of mixed venous blood.
Oh, 75%.
Yeah, it's usually around 60 to 75%, something like that. Exactly. So in mixed venous blood, we take the hemoglobin of mixed venous blood times 1.34 times the SVO2 added to, Jimmy, 0.003 times what?
PV.
Yes, very good. PVO2, the partial pressure in mixed venous blood. So we can look at those two contents, one from the arterial system, one from the Swan-Ganz catheter, and we can tell what the tissue's extracted by taking the content of arterial minus the content of mixed venous. This is 20 minus 15 should be 5 milliliters of O2 per deciliter of blood. So normal content, just get used to it, memorize it. Normal content in the arterial blood is 20 grams percent. Normal content in the mixed venous blood is 15 grams percent. The oxygen extraction is 5. We only use 5 grams percent in tissue metabolism. So the AVO2 content difference, arterial mixed venous content difference, is 5 grams. It's the difference between arterial and mixed venous, or 20 minus 15 equals 5. So it's just a simple difference between what's loaded on the hemoglobin in the arterial system, and we measure that content, minus what we've extracted from the tissues by measuring it in the pulmonary artery in a mixed venous blood gas. AVO2 content difference, or the extraction ratio, is 5 grams percent. There's also another content that we sometimes make sense of, and it's called capillary content. Capillary content, CCO2, is equal to the hemoglobin. Every gram of hemoglobin carries 1.34 milliliters of O2, and we assume that the saturation is 100%. So if we take hemoglobin times 1.34 times 100%, that's times 1, that's by itself, right? Any number times 1 is the number. So we don't make sense of a capillary saturation. We just take hemoglobin times 1.34 added to 0.003 in the alveoli times the P(a)O2. How do we find big AO2? Barometric pressure minus 47 times the FiO2 minus PaCO2 times 1.25. That's the alveolar gas equation. The PaO2 is equal to barometric pressure minus 47 times the FiO2 minus the P little a CO2 times 1.25. Right? So what this does is it sets us up with a way to compare saturations. And typically, I'm just going to skip to kind of the back of the chapter. They look at contents.
I have another one in my erg set.
You had another one here too. But there's just a little small one in there somewhere.
We can sometimes use oxygen delivery to measure something called shunt. And shunt is equal to Q, which is cardiac output. What's a normal cardiac output?
5 liters.
5 liters, very good. Normal cardiac output is 5 liters. So the cardiac output shunted divided by the cardiac output total, or QS divided by QT, is equal to CCO2 minus CaO2 divided by CCO2 minus CVO2. So we can, by using oxygen transport studies, we can get an idea of the amount of blood that was brought to the right side of the heart, moved to the lungs for gaseous exchange, comes back to the left side of the heart and is pumped out to the rest of the body. That percentage is the amount of blood shunted from the right side to the left side without undergoing gas exchange. So a shunt is, let's see. So the percentages of shunt becomes clinically significant. Up to, in most cases we have about a 5% shunt normally. Up to 10% becomes clinically significant. And so from 10 to 20% means there's an abnormality. From 20 to 30% designates significant pulmonary changes or abnormalities like pneumonia, bronchitis, bronchitis, all the lung diseases that cause pathology, that cause inefficient gaseous exchange. And above 30% is life-threatening. Okay? So a shunt above 30%, not a good thing. So I had a patient come in many years ago that she had about a 35% shunt, so she was in big trouble. She was moving blood from the right side of her heart to the left side of her heart through the lungs without undergoing gas exchange. We calculated her shunt to be about 35%. So we had to do specific ventilation strategies on the ventilator to get her past the critical phase. We used 100% oxygen, lots of heat, and a mechanical ventilation strategy to help her to survive, and we did. So, but we did it, we were able to do it by measuring what the shunt was and then developing a strategy to help save her life. So the question was at the time is that Dr. Abdullah came up to me and said, well, I want you to measure her shunt. What percentage of blood is shunted? And we'll develop a strategy based on how high or how low that is. So the higher it is, the more life-threatening it became, and we had to be more aggressive in our ventilation strategy. So I think we put her on inverse IE ratio ventilation and for about 2 days, but she did survive. But we were measuring her shunt the whole way, and we were trying to improve ventilation strategies to ensure that she oxygenated her blood. That was the bottom line. And we did that through arterial blood gases. Yeah.
Is that how you physically measure the shunt?
Yeah. We get an arterial blood gas and a mixed venous blood gas, and we plug it into that equation. Yeah. Capillary content minus arterial content divided by capillary content minus mixed venous content. So we could measure oxygen transport, and that gave us an idea of the percent of blood shunted from right to left of that undergoing gas exchange. So I just want to be clear. Let's see. I think there are some questions that I asked specifically. So a shunt means that the alveoli are collapsed or closed, but you've still got an open blood vessel. So a shunt, let me just write this up at the top. Shunt is perfusion of blood, P-E-R-F-U-S-I-O-N, perfusion of blood without ventilation. So a shunt is when you still have perfusion going past closed alveoli. You want to know what percentage of blood does that. How much alveolar collapse is there that prevents oxygenation? So you have perfusion without ventilation. That's shunt. The other type of abnormality in the lungs is called dead space. And we'll reiterate this in another chapter, but dead space is ventilation without perfusion. So you don't, the blood doesn't go past an open alveoli. So there is a portion of your lungs that are dead space ventilation, and there's a portion of blood that perfuses closed alveoli, or perfusion without ventilation. So we want to know what percentage. Now, like I said, we normally have about a 5% shunt because of arteriovenous anastomosis, because of the Thebesian veins, because of cardiac sinuses that deliver oxygenated or deoxygenated blood to the oxygenated side. Do you remember what that's called? So shunts always result in let's see, what's the term? Shunts always result in it'll come to me. By calculating these kinds of contents, though, it will always give us that measurement. And that's what we're looking for. We're looking for a measurement greater than 5%. Okay. So let's give you an example. Oh, the term I'm looking for is venous admixture. So shunts always result in venous admixture. So there are some deoxygenated blood that enters the right side of the left side of the heart and enters the oxygenated side. That creates a venous admixture. So a shunt of less than 5% is expected. Up around 10% becomes abnormal. 10 to 20 means significant pulmonary shunt, and 20 to 30 means it could be life-threatening, and over 30 you're in big trouble. So let's give you some numbers and let's calculate a shunt. So we would do this with an ABG. So if I have, let's see, let me take this part of it out. So if I draw a blood gas where I'm interested in oxygenation studies, I've got an arterial gas, and then I want in blue. What's the other one? Mixed. They're all green. So arterial, we get a pH, PCO2, PO2, bicarb, hemoglobin, saturation, carboxyhemoglobin, met hemoglobin, and base excess. We'll talk about this one in the end of, probably in 2 weeks, in the end of chapter 6. So in the arterial system, the pH is 7.34, let's say. CO2, 57, PO2, excuse me, 57, bicarb 24, hemoglobin 12, saturation 85, carboxyhemoglobin 0.5, methemoglobin 0.5, and base excess minus 2.2. So this is taken from an arterial blood gas. In the mixed venous system, the pH is 7.33, CO2 is 59, PO2 30, say it's 30 millimeters of mercury. Because we would have expected that the tissues had taken out some of that oxygen, right? So the PVO2, I'm gonna need some more juice. PVO2 is lower than the PO2 because the tissues would have taken out oxygen. Bicarb, 25 mil equivalents. Hemoglobin still 12. Saturation is 51% because the tissues would have taken out oxygen, right? Carboxyhemoglobin 0.5, methemoglobin 0.5, and base excess minus 2.6, 2.5. So those are the kinds of numbers you get with an arterial blood gas, and then you drew a blood gas out of the mixed venous Swan-Ganz catheter that's sitting in the pulmonary artery. Not much difference really in those numbers, right? But again, we're interested in oxygen transport studies from the arterial system versus the one that's in the pulmonary artery. So this is done at, let's say it's at sea level, 760 millimeters of mercury, and the patient's breathing, let's say they're on 60% FiO2 actually, let's do it at a cannula at 6 liters a minute. So what's the FiO2 at 6 liters?
34. 44.
44% FiO2. Anything else we need? I think that's all. Oh, we got the CO2. So, based upon an arterial blood gas and a mixed venous blood gas, I'm interested in transport studies. What I want to do is determine the percent shunt for this patient that's breathing oxygen at 44%. So I can start at, well, I'll ask you, which one do you want to start at? Shunt is equal to the CCO2 minus the CaO2 divided by CCO2 minus mixed venous oxygen.
Find CCO2.
So let's find the CCO2 first. CCO2 in this blood gas specifically is the hemoglobin, which is what, 12? 12 times 1.34. And in the capillary, we expect that it's 100%. So I'm going to times it by 1, which is itself. Added to, this is the amount bound, and this is the amount dissolved in plasma. So the amount dissolved in plasma is 0.003 times the PaO2. The alveolar oxygen level is barometric pressure 760 minus 47 times 0.44 minus the PaCO2, arterial carbon dioxide, is what? 57, no, CO2, 57. 57 times 1.25. So let's do that first. 57 times 1.25. Do you have it, Armando?
71.2.
71. 760 minus 47 is 713 times 0.44. 713 times 0.44. So we're breathing 44% oxygen at 6 liters per minute.
313.
What is it?
72. 313.72.
314 minus 71. 233. Is that right? 314 minus 71?
243.
43.
243. Okay. So I've just calculated that in this alveoli right here, there's 243 millimeters of mercury to that alveolus. So in the capillary blood, I take 0.003 times the P big AO2, 243. So CCO2 is equal to 0.003 times 243. What's that? .243 times 0.003.
.72.
0.72.
Okay. What's normally dissolved in the plasma? 0.3, right? So again, we don't deliver much oxygen in the plasma. This is 0.7. 12 times 1.34.
16.08.
16.1 plus 0.7 equals 6. Is it 16?
20.
16.8.
0.8. So our capillary content is 16.8. Is that good?
It's all right.
It's more than 15, isn't it?
Yeah.
So we're delivering oxygen to the tissues. It's at least higher than 15. We're not hypoxic per these standards. Even with a PO2 of 57 and a saturation of 85%, we're not hypoxic. We still have a fairly high capillary content. Okay? So you see how we got that? Capillary content was calculated to be 16.8. So it's going to be the same here. Now I have to calculate the arterial content. So the arterial content is the hemoglobin, which is 12, times 1.34 times the SaO2. What's the SaO2? 0.85. 12 times 1.34 times 0.85. It's going to be 16.8 times 0.85.
13.6.
How many?
13.6.
Ooh, 13.6. So you can see what saturation does to overall oxygen delivery, right? It really reduces that. At 85%, it really reduces oxygen transport to the peripheral tissues. Added to 0.003 times the PaO2 in that blood gas says 57. 0.003 times 57. So that's 0.16. So the capillary, or the arterial content is 13.6 plus 0.16 equals 13.7, almost 8. So the arterial content is 13.8. So I'm measuring oxygen transport studies from the capillaries, what happens at the alveolar capillary membrane, and what's in the arterial system, the oxygen content in the arterial system. Now I have to measure the mixed venous content. So mixed venous content, CVO2, and notice all I'm going to do is I'm going to change the SA to the SV and the PA to the PV. Make sense? So what's the mixed venous hemoglobin?
12.
Times 1.34 times the saturation of mixed venous blood. Yep. 0.51. Added to 0.003 times the PVO2. Here's the mixed venous blood. PVO2 is 30. 0.003 times 30 is 0.09. 12 times 1.34 times 0.51. Thank you. 8.2 plus 0.09 is 8.3 for a CV, a mixed venous content. So I've just measured from the pulmonary artery a blood gas that measures oxygen transport that came back to the right side of the heart after the tissues have extracted oxygen out of it. So now I've got this value right here, 8.3. So basically I just plug the numbers. 16.8 minus 13.8 equals 3 divided by 16.8 minus 8.3.
8.5.
How many?
8.5.
Thank you. 3 divided by 8.5 is what?
0.35.
How are we doing in terms of oxygen content studies and shunt?
So we've
How do you clinically draw any conclusions about that? The amount shunted,
got,
which is the amount of alveoli that looks like this, that is perfused without ventilation, that's a shunt. Perfusion without ventilation. 35% of the blood isn't exposed to alveoli that are open. Is that a good thing or is that a bad thing? It's a bad thing. Over 30% is life-threatening. So we just calculated a patient based on oxygen transport studies of content showing that a shunt here is 35%. And we better come up with a strategy to save his life or he's going to need his or her maker.
So you're saying 35% of the oxygen is not exposed to the alveoli
Yes, 35% of the blood
of the blood?
isn't exposed to alveoli that's open. And so we have a 35% shunt, which is significant and life-threatening. And we better come up with ventilation strategies to start opening up shunted alveoli. Alveoli that are not ventilated but still perfused. And we can do that. We can put a patient, we can put them on an ET tube, put them on a mechanical ventilator and use positive pressure to force air in and to allow it to come back out. But we're going to do it under, we'll probably have to sedate the patient. We may have to use inverse IE. They might want to use a high frequency oscillator. But they have to use a strategy that's going to reduce the shunt from 35%. Go ahead, Armando.
One of the definitions I got for shunt was that they're perfused but not ventilated, but it said because of fluid in the alveoli. Is it always fluid or sometimes it's not fluid?
It could be from any
It could be
reason.
anything.
So the main thing is that the alveoli are not participating in gas exchange.
Okay.
So we have to ensure that they participate. And we usually put an endotracheal tube and we use, you've talked about this in lab, right?
Mm-hmm.
We use PEEP. We use positive end expiratory pressure so that the pressure inside of here opens those up. We do that with simple breath holding for patients with postoperative atelectasis. Taking a deep breath and holding it through collateral circulation through pores of Kohn and canals of Lambert, we pop open previously closed alveoli. So we can do that on a small scale. On a large scale, in critically ill patients who have large shunts, we have to use mechanical ventilators and ensure that their alveoli are open so that they participate in gas exchange. And we usually use pressure, either non-invasive ventilation or we put an endotracheal tube down and we expose them to positive. Now there are inherent risks to that, and we'll talk about risks. The most important one is exposure to pressure is called barotrauma. So if you've heard of that term before, it means exposure to pressure. There are problems with barotrauma. So if we use positive pressure inside of the airway, that minimizes venous return, it limits cardiac output, and reduces then perfusion, not only through the lungs, but everywhere else, specifically the kidneys. And one of the first things we see is patients will reduce their urine output and by release of ADH, and ADH will cause us to hold on to fluid. And so our urine output will drop below 20 milliliters an hour. But that's the physiologic risk of having to use pressure and barotrauma by encouraging oxygenation, but then we limit kidney perfusion. So it's a complication associated with the very treatment to encourage a better shunt. Interesting. There's always a balance. Anything we do in practice always exposes patients to a risk, whether it's infection, whether it's barotrauma, whether it's reduced renal function. There's always a trade-off, and we have to balance the risks with the benefits. Like any drug, there are always inherent risks. We have to minimize what we do. But here's an example how we use oxygen transport studies in the care of a patient with a large intrapulmonary shunt, more than 35%, that we have to use positive pressure strategies of mechanical ventilation to reverse that trend, save their life, but then there's always hemodynamic consequences. So we're often faced with this risk, and we have to balance the benefits with the risk and try to come up with a strategy that we take both of those into consideration. So just by using pressure, I mean, if we treat this and we go down to 20%, we might have influenced cardiac output by encouraging more pressure than the heart could stand. And now they're in hemodynamic compromise because of the pressure we need to use to open up alveoli that were previously closed. And like I said, that's always an inherent risk between the treatment and the benefit of that. That's a shunt. So there's always one bonus question on the end of every test.
Do all of that calculation.
Holy shnikey.
Are we gonna have to learn all these
Shunt
equations?
equation.
Oh my gosh.
Now, the good news is, Armando, that most blood gas labs have a computer program that you just punch those in and it'll calculate.
And it'll calculate, I love technology.
Yeah, but this is where it comes from.
Yeah.
This is what they're using to make that assumption, to make that measurement, is they use that shunt equation.
So like, are we gonna have to know like the CCO2, PaO2, or are those gonna be already like given to us?
You can calculate them.
Okay, so we're gonna have to calculate all, so we're gonna know multiple equations for this one equation.
Interestingly enough, content, arterial content, mixed venous content, capillary content are all the same thing. Hemoglobin times 1.34 times the
Just times the
saturation.
saturation.
Is that the
0.003 times
CCO2 though?
PaO2, PVO2,
It uses the alveoli.
P big AO2.
Okay.
Yeah.
Same equation. So you don't have to, you just know one equation, know the content equation, but be able to arrange it to arterial, mixed venous, and capillary.
Material mixed.
And there's another one, there's the arterial gas, the arterial air equation.
Or the CCO2.
CCO2 is the alveolar
Yes,
oxygen equation.
Not one, there's two.
Did you say in content?
So, like I said, luckily, most blood gas labs
Why do you
will
remember
have a
the
computer you can
1.34?
you can
That's
punch
nice.
these numbers in. But then again, the blood gas
You know what?
Blood gas will generally have a CaO2 for arterial, it'll have a CVO2 for mixed venous, and it'll show up on that blood gas. You'll still have to do the CCO2 and the P big AO2.
So we'll definitely get these values and then
Yeah.
just plug
Are
them
you
in.
gonna put this
You just
video
plug
up?
them in.
Yeah.
But this is where it comes from.
That'll be a good
So in
video
order
to
to
look
look
at.
at oxygen transport, we need to know how much oxygen is shunted from the right side to the left side of the heart without undergoing gas exchange. That percent shunt is indicative of the degree of intrapulmonary influence. And that degree of influence can be quantified for pneumonia, for bronchitis, for bronchiectasis, for silicosis, for asbestosis, for bronchiolitis, for bronchiectasis. I mean, all of the pulmonary disease, we're interested in oxygen transport. And if we know these, that will help us to quantify the degree of shunt. Go ahead, Kyle.
Does the mixed venous blood always have to be taken from pulmonary artery? Can it
Yes.
be taken from the Like a PICC line?
Yeah,
Take-
always from the pulmonary artery.
Always.
It's always been pulmonary.
Yeah.
artery.
So a PICC line.
PICC line
draw-
is venous, that's straight venous.
Okay.
So it's not exactly the same thing as mixed venous. Mixed venous means pulmonary artery
Okay.
specifically. A PICC line is strictly venous, and the CO2s will be higher, the pHs will be a little bit lower. So it's not exactly from the Swan-Ganz catheter. So mixed venous will always be from a Swan-Ganz, Hannah.
Actually, I can wait.
Oh, okay. Go ahead.
So if we're doing this equation to find out the difference, like how much oxygen's being consumed, they would never just use a venous sample, right?
No, they'd use a mixed venous from the Swan-Ganz catheter.
Okay.
Okay? Is that too much to kind of absorb?
Kind of.
It's interesting that we're only making a discernment of partial pressure, which is a result in hypoxemia, or hypoxia, which is more content-driven, how much we actually send out to the tissues and what the tissues then send back. Okay? We only use a quarter. So in the back of the text, I'm looking on, they look at a few oxygen transport studies. So I'm looking on page, oxygen transport calculations 274. Total oxygen delivery, this is how much we send out. So the oxygen delivery is equal to the cardiac output, so the 5 liters of circulating blood in the circulation, times the content times 10. So if normal content is 20, total oxygen delivery is about 1,000 milliliters. So CaO2 normally is 20 milliliters of O2 per deciliter of blood. If we take that times 10 plus the cardiac output, let's see, QT. So the oxygen delivery is 5 times 20, which is about 1,000 milliliters per minute. So if our content is 20, then every minute we send out 1,000 milliliters of O2. That's oxygen delivery. And all we do is we take our content times the cardiac output. So I don't want us to learn or memorize these mathematic equations, even though they give them to you. I'm just giving you a definition. Oxygen delivery is the amount that we send out per minute, and it's equal to about 1,000 milliliters.
That's the total oxygen.
Oxygen consumption, on the other hand, down at the bottom of that page, oxygen consumption is called VO2. So V with a dot, O2 is how much oxygen we consume in 1 minute. And remember I said that normal oxygen content in the arterial system is 20, right there. Normal oxygen content is 20. So remember how I said that we only use a quarter of what we send out? So that means that what comes back is around 15 volumes percent. That's the arterial minus the venous content. AVO2 content difference is 5, so we use 5, and that's 25%. So the oxygen consumption is the AVO2 content difference, which is about 25% of what we send out. Okay, so oxygen consumption is the amount of oxygen extracted by the tissues in 1 minute, which would be what? 250 milliliters. So typically speaking, your tissues will take out about 250 milliliters every minute. VO2 is 1/4 of what we send out, which is 250. So oxygen consumption every minute is around 250 milliliters. Okay, this will be important when we start thinking about RQ. In another chapter, we'll look at the respiratory quotient, which is VCO2 divided by VO2. So we produce 200 milliliters of CO2, and we consume 250 milliliters of O2. And so RQ is equal to 0.8. So we'll make that connection here in another week or two. So again, oxygen transport studies, we can manipulate what we know about how we combine oxygen, how we transport it, dissolved in the plasma, bound to hemoglobin, and then knowing about what we deliver, what we extract, we can make some assumptions about how well the human body is performing those functions. So total oxygen delivery, oxygen consumption is 25% of that. AVO2 content difference is 20 minus 15. Normal arterial content minus mixed venous content, 20 minus 15, is 5. So we know that the tissues for normal metabolism will take out 5 grams per cent. What else? Oxygen extraction ratio. So at the top of page 278, extraction ratio is the CaO2 minus TbO2 divided by the arterial content. And that's 25, that gives you the 25%. So not only does the total oxygen delivery of 1,000, the oxygen consumption of 250 milliliters reflects the fact that we only take 25% of our oxygen out of the arterial blood, which is oxygen extraction ratio, 25%. Mixed venous saturation is the saturation in the pulmonary artery. It's usually between 60 and 75%. The average is probably around 65. And then we'll talk more about shunting next week. So let's take a short break. I want to come back and talk about the oxygen dissociation curve, what that shows.